So it's too loud. So I'll start with the setup. So we have a complete discretely valued field with ring of integers OF, and I'm going to choose a uniformizer pi f OF and I'm going to just write the residue field by k, and then I'm going to assume k is algebraically closed with positive characteristic. So f can be mixed characteristic or equal characteristic, but I really want k to be positive characteristic for reasons I will discuss later. And I have G over OF, a split reductive group. And, well, so inside here I have G, I choose a Borel, and I choose a torus inside that. And then once I choose all of this, I can now look at this other Iwahori group scheme, I mapping to G, where I is a dilatation of G along B, the spatial fiber of B, and then it'll satisfy this property that I of OF is the kernel of, maybe I shouldn't say kernel, but well, let me just write it like this: the kernel of G of OF projecting to G of K mod B of K. Okay, so now I want to, well, I think, try this. So what did geometrics of Hecke say? It was something, an equivalence of the form, I look at perverse sheaves on L plus G mod LG mod L plus G with coefficients in, actually let me call this Hecke G, with coefficients in some lambda being QL bar. So this was equivalent to, let me write it like this, the coherent sheaves heart on the B of G check, or G hat, where G hat is some, the geo group over lambda. And now I want to sort of, well, try to do this for Iwahori level, so L plus G. So what I want to do is, the question is, what is the spectral interpretation of something similar for but Iwahori level? So in this case, actually, I think better to look at all sheaves instead of just perverse sheaves. And I'm going to look at L plus I, which is something contained in L plus G, and L plus I, with, again, lambda coefficients. And the goal is to try and have a spectral interpretation of this QL bar. And let me also call this the Hecke stack for I. So that's going to be the main topic of the Bezrukavnikov equivalence. So I need to tell you what this is going to correspond to on the spectral side, but before that, I think it's probably wise to briefly review the Bernstein presentation, which tells us what this thing looks like if I don't categorify and just look at the actual Hecke algebra. So So what are the points of Hecke I? So if you just look at the double coset I of OF, mod G of F, mod I of OF, so if you think about Bratti's theory, it's going to be, it's going to be very much related to the space of alcoves inside a single apartment, and is isomorphic to W hat, which is also isomorphic to N, the normalizer of a torus. I take F points, and then I mod out by the OF points of the torus. So these are all isomorphic, and this sits as called the extended affine Weil group. And it sits in a short exact sequence of T to W tilde to the finite Weil group corresponding to the, which is the normal Weil group you think about, which also has a section coming from the choice of my hyperspecial point. So the points are going to be something that's basically a lattice together with some finite group. So it's going to be finite, well, a finite disjoint union of a bunch of lattices. So this, because of this description, if I look at the Hecke algebra, which is given by the continuous, compactly ordered continuous functions on the double coset. This has a basis given by the indicator functions of all of these double cosets. W I of OF. And and you can try to think about what kind of relations these have. There's kind of some, if I have two elements of W that if you multiply them, the lengths add, then the convolution of the two things will be the convolution of the, will be the new indicator function and so on. So it does give us some presentation. It gives a presentation. But I want to look at another presentation called the Bernstein presentation. So what I'm going to do is to define theta of lambda to be the indicator function of I of OF times lambda of pi f. So now lambda is a cocharacter, so I can plug in pi and get a new element of GF. So I can do this. And sorry, lambda is a cocharacter that is anti-dominant. T minus. So in this case, I can define this double coset corresponding to this lambda, and then define element of the Iwahori Hecke algebra called theta lambda. And it satisfies the property that it's multiplicative as long as I stay in this anti-dominant cone. So if I define this, I can extend to all cocharacters lambda by defining lambda in all of the cocharacter lattice by declaring that if lambda is lambda 1 minus lambda 2, where lambda 1 and lambda 2 are both anti-dominant, then I'm going to define theta of lambda to be theta of lambda 1 times theta of lambda 2 inverse. So this is a thing I can do, and then this gives me a algebra map from lambda, the group algebra for the cocharacter lattice into the Irohori Hecke algebra, sending the generator lambda to theta of lambda. And the, well, one of the consequences of the Bernstein interpretation is that if I look at, well, first of all, this is a commutative subalgebra. This is defines a commutative subalgebra of the Hecke algebra, and the center of the Hecke algebra is exactly the finite Weyl group fixed points of this under this taking linear combinations of thetas. So that's going to be so this is what the Bernstein presentation gives us, and essentially in our analysis of the categorification of this, which is the sheaves on this Hecke stack, we're going to see these kinds of objects appearing. So I briefly wanted to mention this before moving on to the actual statement of the Bezrukavnikov equivalence.
So is there any reason why we're using anti-dominant?
I think it's a convention. I think. Right, so why is that true? So the point is that if lambda is lambda 1 plus lambda 2, and lambda 1, lambda 2 are both anti-dominant, well, the lengths of lambda 1 and lambda 2 add up to the length of lambda, and so theta of lambda is theta of lambda 1 times theta of lambda 2. And this implies that if I define these things as, right, if I add both lambda 3 to both lambda 1 and lambda 2, then I can cancel out the lambda 3 and the lambda 3 inverse. So it is something that's well defined, and it's going to be commutative almost by construction.
Why should theta of lambda 2 be invertible?
I think it's not too obvious, but I think it turns out to be true.
Wait, no question. This is a unital algebra, right?
Yes.
No question.
Okay, so now let me try to describe what should be going on the spectral side. So again, what we wanted to do is to understand, so on the geometric side, we want to think about sheaves on this Hecke stack with lambda coefficients. And I'll say a little bit more about what I mean by sheaf later on, but this is also going to have some monoidal structure. And on the spectral side, we want to realize this as a category of coherent sheaves or something similar on some dual group, some geometric objects involving the dual groups. So we have this Langlands dual group G hat containing B hat, containing T hat, everything is pinned, over lambda equals QL bar. And let me just make a bunch of definitions. So I'm going to define curly U as something inside G hat consisting of unipotent elements. So scheme theoretically, I can describe it as I look at the G hat mapping to G hat, GIT quotient G hat by the adjoint induction, and then I'm taking the fiber of the identity point. I'm taking the reduced fiber of the identity point. So it's going to be some close-up variety. And this has a nice resolution called the Springer resolution. So what I'm going to do here is I take U tilde to be G hat times B hat U hat, where the action here is right translation. And the action here is conjugation. And then this is going to be also have the interpretation of I'm taking pairs of elements G and let me call it B hat prime, where B hat prime inside G hat is some Borel, and G is something inside the unipotent radical of B prime. Unipotent radical of B prime, B hat prime. And so this is going to be some subvariety. It turns out to be smooth. And then I have this map down to U, sending G comma B hat prime to G. And that's going to be, turns out to be a resolution of U by, in the sense that it's birational proper and the thing on the top is smooth. So I have this thing. It's a little bit less clear what the motivation is, but it turns out to be the right object to look at. And it's slightly different from the usual treatment of Bezrukavnikov in the sense that you usually use the nilpotent cone inside the Lie algebra. Here I'm using the unipotent subvariety, but well, in characteristic 0, which I'm assuming they are related by the exponential map, so it's not that much of a problem. Okay, so, but here I'm also going to look at a larger thing called the Grothendieck-Springer resolution. So again, I'm going to use the multiplicative version. So I have G hat tilde. I'm going to define it as G hat times B hat, which is, again, the B hat action on the G hat side is going to be right translation. B hat action on the B hat is on the right side is going to be conjugation. And this has the interpretation of being, again, the same thing. You have B hat prime of Borel. And then I want G to be inside just B hat prime instead of the unipotent radical of B hat prime. And so everything is sort of includes here. Includes a unipotent version. And then this, again, maps to G hat. Just by forgetting the Borel that it contains. And that's going to be a alteration. So this is called a Springer resolution. This is called a Grothendieck-Springer alteration. And then, so I'm still continuing on defining some random varieties. So, and then I'm going to define this thing called the Steinberg stack, or the Steinberg variety. So the Steinberg variety is going to be, well, let me define the Steinberg stack first. It's called, I'm going to denote by S of G hat. I'm going to define it as, well, the more concrete description is going to be I take U tilde and then take U tilde and take the self product over G hat. And the reason I want to take the fiber product over G hat instead of over U is because I really want it to be a derived fiber product. And that's some derived scheme, and then I take the quotient by the G hat action acting on everything equivariantly. So, right, so I have this Steinberg stack. And I can also write this as U hat mod B hat times G hat mod G hat of U hat mod B hat. So it's another way of writing it. Again, I should put a derived here. And it's, you can check it's the same thing. And this part is called the Steinberg variety. And I'm also going to consider a slight thickening of this. So instead here, it's, this is the unipotent part. Yeah.
What's below this last product is, what is
Here,
Yeah.
it's a G hat mod G hat by, yeah, G hat mod G hat where the action is conjugation.
Are these, the left and right side, are they like U tilde or U hat?
Sorry, these are all U hats. Sorry. This is a U hat. This is U tilde. Sorry. This is U tilde.
Now they're distinct.
Yeah, these are U tildes, these are U hats. Okay, and so this is a Steinberg stack. I also want to look at the slight thickening of these things. So here, what I'm going to do is to take the formal completion of the following thing. So instead of looking at U hat times U hat over G hat, I'm going to take their formal completions. So, oops, sorry. So I'm going to take G hat tilde times G hat tilde over G hat, and then take the formal completion over the smaller thing, U hat times G hat. So U tilde times G hat, U tilde. Sorry. And, well, so this is a formal thickening, but I'm still quotienting by G, and I can also think of this as U hat, so, well, maybe B hat, I formal complete along U hat. Okay, I didn't think it was so hard to write this, but it's, I'm taking B hat and then taking the formal completion along U hat, and then taking the conjugation by B hat. And I'm going to do the same thing on the other side, B hat, U hat, formal completion mod B hat, and take the fiber product over G hat mod G hat. So, so again, this is a very concrete variety, well, a very concrete formal scheme quotiented by an action of G hat, which is a reductive group. It's the same thing copied, but I didn't have enough space. Yeah. Should I rewrite it? Okay. Yeah, and a small remark is that on this thing doesn't require a derived fiber product. So this is some fact about how you can calculate the dimension of these varieties and its expected dimension, so it turns out to be something LCI, and then it doesn't require a derived product. So, so even if this, the maps are not flat, but still there's no derivedness in this fiber product. Okay, so any other questions, including notational or?
Very naive. If you describe this as a resolution, was something in this picture singular, and this is the resolution of that?
Yeah, U is singular. This nilpotent, unipotent elements.
You mean that thing that has an arrow saying smooth variety?
So U tilde is smooth. U is singular. So if I look at the
U is singular.
right, so and then U tilde is a resolution of U in the sense that it's a smooth thing itself mapping to something singular, and it's birational improper.
Was there a U without the hat? Sometimes there is no U without that.
So maybe there is a U without the hat, which is supposed to be the unipotent elements inside G hat. And then U hat is supposed to be, I didn't write this, but this is supposed to be the unipotent radical inside B hat.
Here's right there.
So this, yeah. So, okay. Sorry, when I was writing notes, I had a calligraphic U, so I. Okay, sorry. Maybe I'll do a very simple example for SL2. G hat equals SL2. This U, which is unipotent elements, is going to be some unipotent matrices in SL2, which is going to be a cone. And then there's a resolution U tilde, which is it basically blows up the points, the singular point, and it becomes some. It's a total space of some vector bundle on P1, and then it becomes smooth. Alteration just means it's generically finite, and the total space is smooth, and the map is proper. Yeah. So this G hat tilde is finite to 1 generically, and the generic degree is going to be the size of the Weil group. Okay. Sorry if this is a lot, but it's kind of a bunch of unmotivating definitions that turn out to be the right thing, and it's kind of hard to explain why. At least I don't see a very good intuitive explanation for why these are the correct objects. Okay, but let me continue. So what is the thing I want to look at? So let me just state the theorem, which is the Bezrukavnikov equivalence. So it was proved by Bezrukavnikov for equal characteristic, and then for mixed characteristics, this was proved by Bando by somehow comparing this with the equal characteristic situation. So it's sort of bootstrapping on top of the equal characteristic theorem. And then there's also some Betty setting that was proved by Dillon and Taylor. Which states that, well, first of all, so on the geometric side, I'm looking at sheaves on this thing I'm calling the Hecke stack of I, which was defined to be L plus I mod LG mod L plus I. And this is monoidally equivalent to in the co of the Steinberg stack. I'm going to try and write hat instead of tilde. And then technically, I think I need to put a end sheaf, find FG here. So there is so the theorem states that there is a monoidal equivalence between these two categories. And well, so what's the point of doing this? The point is that if once I have this statement, well, hopefully it's, you can imagine there's some Frobenius action on both sides. And then if I somehow take the categorical trace, well, then I'm going to get categorical local, or at least unipotent categorical local Langlands. Well, I mean, it's not the reason one would care about this, but it's definitely, I think, the reason this is included as a topic in this summit. And this is basically going to be the topic of Xin-Wen Zhu's course next week. So, right, so the point is that if I have this monoidal equivalence, I can take the categorical trace to get this. And I also need to state one other thing, which is used to prove this. Yeah. Is it clear that it's which side? Okay, I guess Xinyu is saying no. So I guess. Okay. Okay. Well, maybe I'll. Okay. Yes, we can have a Q&A. Yeah. Sorry, I'm not really the expert too. Yeah. Okay. So. Right, so that's a statement, at least an equal characteristic that well, hopefully we'll see some ingredients of the proof for. Okay, and to prove this, we actually have to do something a little bit more complicated. So, which is to actually do add this monodromic sheaf version of this entire picture. So there is something I'll call Hecke IU, which is going to be some L plus IU mod LG mod L plus IU. And on the Steinberg side, I'm going to look at the formal completion of the Steinberg stack, which I've, in co of that. And so that's going to be the monodromic version of the Bezrukavnikov equivalence, and then somehow we're going to recover the original with a more intuitive Bezrukavnikov equivalence by taking some procedure which involves killing monodromy. Everything is derived. It's a good question. Is there an exotic T structure on the right side? It's not T exact. Okay. Cool. Okay. So this is not completed. So let me try to explain a little bit about okay, sheaf. So first of all, let me try to define what L plus IU is. So IU is so here is a further dilatation of I, so that IU of OF is the kernel of G of OF to G of K mod I of K, U of K. Sorry?
I guess you just want the preimage of UK, right?
Yeah, I use this abusive notation. Yeah, sure, yeah, yes. Yeah, so I'm looking at the preimage of U under this. So it's so this Hecke U IU over Hecke I is going to be a TK times TK torsor. And then I can define, well, so here I'm really using sort of the U monodromic. So first of all, the definition I'm going to just use for simplicity is that sheaf mon of Hecke I U is a full subcategory of all sheaves on Hecke I consisting, well, generated by pullbacks from, sorry, this is U, pullbacks from Hecke I. So it's really the sort of unipotent monodromic things. And what is sheaf? So this is a secretly co-sheaf. So we're going to use the sort of the Schrieg sheaf theory. So for finitely presented things, I think this is something that Mingja briefly discussed. For finitely presented X, sheaves of X is the usual thing. For algebraic spaces, you define sheaf of X to be the colimit along so colimit of y, sorry, x to y of sheaves of y. So basically do a left con extension along Schrieg pullbacks, and then for general, you define sheaf of x to be the right con extension. So it's some sheaf theory that makes Schrieg pullback always exists. And star pullback exists for, what was it? For end perfectly finitely presented morphisms. Perfectly finite presented. And so there's no constant sheaf in this theory usually. So because we can't star pullback from a constant sheaf on the point. We only have the dualizing sheaves, and sometimes there are no constant sheaves. Well, usually there are no constant sheaves. So that was some aside on the precise definitions of everything on the left side. And then what is a monodal structure? So the monodal structure is going to be given by, well, if I have Hecke I, which is, well, Hecke I times Hecke I can also write this as BL plus I times BL plus LG, BL plus I times BL plus I times BG, BLG, BL plus I over lambda, I guess. And then I'm taking a diagonal from BL plus I times BLG, BL plus I, BLG, BL plus I. And then I also have a projection to the first and third components, so I have a BL plus I times BLG. Sorry, I'm running out of space. L plus I. And then I'm defining F star G to be, I take F box tensor G, and then I take a shriek pullback of the box tensor along diagonal, and then I'm taking a star push forward along that. And this is well defined because the affine flag varieties are in projective. Okay. Right, so that's going to be my monodal structure on the geometric side. On the spectral side, I'm going to do a similar thing. Similarly, because I have this product decomposition, well, I can write the Steinberg stack as something like U hat mod B hat times G hat mod G hat, U hat mod B hat. I can do this kind of convolution product structure and do a star upper shriek, P lower star convolution. And that defines a monodal structure on the spectral side as well. And well, for the monodromic versions, you kind of do a similar thing. One thing I should also say is what is in co. So for the non-monodromic version, it's just a Artin stack. So this is end of co for these finitely presented Artin stacks. For the formal completed version, we have to take the star push forward colimit. So in the co of SG hat formal completion is going to be you write the formal completion as increasing union of actual schemes living inside SG hat completion, and then you take in co, and then you take the colimit as a star colimit along the star push forward maps to get this. And again, there's no structure sheaf O in this setting. You only have dualizing sheaves. So you can think of it as coherent sheaves. Well, you think of it as, I think you can also think of it as quasi-coherent sheaves. On on this thing before taking the formal completion, supported on the nilpotent things. Sorry, the unipotent things. No, it's
Then I think you should say
yeah.
there is this info has some lazy meaning. So it's like
Okay, yeah. Okay. Okay, I'm forgetting if it's quasi-smoothness helps, but okay, let me write in co. Yeah, thank you. Okay, so that's the statement of the Bezrukavnikov equivalence. So you have some incoherent sheaves on the Steinbergs, or it's a completion of Steinbergs. And on the other side, you have sheaves on the Hecke stacks both with convolution modular structures. Okay. Should I, do I have until 35 or 45? 45, okay, thank you. Okay, so I think I should start discussing some examples of this, what objects look like on both sides, which is also going to help discuss the, help me for the archetypal Bezrukavnikov functor. So, so the first thing I want to talk about is standard and co-standard sheaves. So this is pretty simple. So, well, if I have my flag variety, well, I have already said something about if I take I plus u mod LG, sorry, L plus u, so L plus I mod LG mod L plus I. If I look at the topological space, this is identified with the affine Weil group. And so, given an element inside the affine Weil group, I can look at the corresponding stratum given by Hecke I, comma W, and living inside Hecke I. Let me call this inclusion I of W. And then I can just define the standard and co-standard as, if I look at this is the standard sheaf is going to be defined as, you look at IW, and then you push forward something along this, but I can't put a constant sheaf on the Hecke stack because constant sheaves don't exist. So I need to put the dualizing sheaf of the Hecke stack over the point K, and then I need to do a bit of a shift. So I think I need to shift by negative L of W here. And similarly, I'm going to define the co-standard sheaf as IW lower star of omega Hecke IW shift by negative L of W. Okay, so that's the one on the usual Hecke stack, but then I need to define some monodromic variant. So what I have to do is to look at the corresponding thing. So, so if I choose a lift, W dot inside the normalizer of F, F point of the normalizer of the torus, then there is a corresponding projection map. I think I don't have time to explain, but there's a corresponding projection map from Hecke, the corresponding unipotent, well, the Hecke U version of the stratum mapping to Tk. And then I can define the monodromic versions as delta W dot mon as I similarly take IW, the U versions, and I push forward the projection W dot, pullback of the rank 1 co-free monodromic sheaf. This is an inside sheaf of T called a co-free rank 1 monodromic sheaf. And then I need to, again, shift by L of W, negative L of W. And again, I'm going to define the same thing for the co-standard version, IWU, lower star of the same thing. And so these, I claim, roughly play the role, well, the deltas roughly play the role of the thetas from before. So there's a proposition. So these sheaves, delta mon and nabla mon are perverse with respect to a perverse T structure given by you pull back to the flag variety and then you say the usual things up to some shift. And they're non-canonically independent of the choices of lifts, and there's also, moreover, if L of W1, W2 is L of W1 plus L of W2, then I have delta, if I take the standard sheaves and then I take the convolution of the two things, it's going to be isomorphic to the, if I multiply the corresponding lifts and then take the monodromic sheaves over there, and then I also have this similar thing for the co-standard sheaves as well. And moreover, if I have, if I try to calculate the convolution of the standard with the inverse co-standard, that's going to be the monoidal unit, which is delta 1 mon. And similarly, for if I take the co-standard, I convolve with the standard. Okay, so what does this buy me? So if I fix fix a uniformizer pi f inside O of f, and then if I choose the representatives of my extended affine Weyl group elements, well, at least for those inside the co-character lattice, as you apply the co-character lambda to pi of f, then what I have is that, so for lambda inside the dominant ones, define J mon of lambda to be, sorry, maybe I'll just do it in general. So for lambda, any co-character, write lambda as lambda 1 minus lambda 2, where lambda 1 and lambda 2 are both dominant. And then I can define J mon of lambda to be the co-character for lambda 1 of pi f. That's going to be some representative lifting lambda. And then I convolve it with the minus lambda 2 of f pi f on the, so I'm convolving with the standard thing on the other side. And that's going to be, again, well-defined. And it's going to lift to a monoidal functor called J mon from rep of t hat, because that's going to be graded for, right, so co-characters of t are characters of t hat, so that's so it's this side, so rep t hat to the sheaf mon of the Hecke stack, basically given by this above formula. And these are called Wakimoto sheaves. Let me end by saying what these things correspond to under the Bezrukavnikov equivalence. So under the Bezrukavnikov equivalence, this J mon of lambda corresponds to the, so I first look at the diagonal push forward of some sheaf on B hat U hat wedge mod B hat into the Steinberg completed. So there's this closed embedding, or well, there's this map. And then I am going to look at the push forward of omega of B hat U, this formal completion mod B hat, and look at the dualizing sheaf of that. I'm going to twist by lambda as coming from, regarded as a representation of B hat, and then I'm going to twist by this line bundle, and then I'm going to take the diagonal push forward of that. So, so this is how at least these Wakimoto sheaves look like under this Bezrukavnikov equivalence. I think I'll have to stop there.